Okay, welcome back everybody. Today we will continue with bitmap indexes. This is part 2. So we had part 1, then there was a Christmas lecture, now it's part 2 of bitmap indexes. Maybe we also go back to what I did in the Christmas lecture because I used stuff. I will actually explain today in more detail, Bloom filters. It's a variant of a bitmap index. So far we only looked at uncompressed bitmap indexes. And as a reminder, that's basically what we talked about a couple of weeks ago. So we have a table with 3 columns here, colleagues, and on the cities column, on the city column here, this one, I create a bitmap index. The bitmap index, just for terminology, consists of bit sequences. A sequence of bits being set here represented as 0 and 1, could also be true and false, of course, that's what it is about technically. So it's Boolean values, of course. And then you always set this value if that value in New York appears in the city column. So for each distinct value appearing here in the city column, you create one of those bit sequences. So the number of distinct values you find here determines the number of bit sequences in your bitmap. Yeah, we discussed about that, the trade-offs. Of course, that also implies that if you have many duplicates here, what is going on here? If you have many duplicates here, then the bitmap is very efficient because you don't need so many bit sequences and so forth and so forth. Yeah? Then you can do the math, how many bits do you have to represent, and all of that fluff we discussed already. So this is an equality bitmap index or equality bit lists, but you can also use other variants of that. What's going on here? And that was this predicate-based bitmap indexes. This was an example for that. So here the semantics of a single bit list, aka bit sequence change. Here the semantics is not equality as used before. So that's still the an example bitmap for equality. But here why isn't this working anymore? Oopsala. To the left. Okay. Here, the semantics is the value smaller or equal? Yeah, and you can play all kinds of games with that. We talked about different queries you can answer with that, and so forth and so forth. So today, we will look at how to compress these bitmaps, yeah, how to save space. And because when you look at these bitmaps, you will see, okay, there's so many zeros, so many bits are set to false. Is there a way to meaningfully compress these bitmaps and still be able to do query processing? That's one thing we will be looking at. But one other thing, just for you as a reminder, I mean, who of you already worked with pandas? Pandas? A couple of you, because there you see bit sequences and bit lists already. Here's a simple example I prepared. So basically here I'm loading this infamous iris data set, yeah, petal width, sepal width, tra-la-la-la. So it's one of the most widely used data sets in machine learning. People train all kinds of classification models on that. And when you look at the type that's being created here, that's a data frame. This is not the relation in the relational sense. It's really something different. Don't get me started about that API, but it's widely used. But then when you do stuff like this here for instance, I'm saying, okay, on this column, I want to have all the values that are equal to 3.8. What is returned is actually what we are calling in this lecture a bit sequence. Yeah? So for instance, if I print that to the screen here, you will see a lot of false and true values. For each row in the input, you determine the result of this predicate. Is it true or false? So what we get here is basically a bit sequence, the same thing. That's how you select data, that's how you filter data in pandas. Yeah? And you can do that for all kinds of conditions, like here. And then you apply the bit sequence to the actual pandas data frame. That happens here. Yeah? So in square brackets, you now say, okay, I want to have all these entries where, what did I use, where the sepal width equals 3.8. And if I do that, I only get those rows. Yeah? Yeah, that's what I get here. Or for the second condition, where the petal length is 1.9. If I apply that here, that's what I get. And of course, you can combine them through a Boolean bitwise AND, yeah, and then you get something like that. That's already where you operate with bit sequences. So, yeah, that's how pandas decided to do that, just as a footnote. Okay, so let's look at compressed bitmaps. I extended this 11a data set a little bit, so you should update that. I added a couple of slides and clarifications here and there. Let's swap again. So that's 11a again, so there's 11a, 11b, and 11c in our CMS. So we looked at uncompressed, and now we look at compressed bitmap indexes. And there are two types of compressed bitmap indexes. The one is lossless, yes, you don't lose any information, and the other is lossy. And we will first look at lossless, and in particular run length encoded, and then word aligned hybrid, which is an improvement over run length encoded. But run length encoded is already interesting and important to understand. Yeah. So how you could imagine that is that so previously when we looked at these definitions for bit sequences, we really defined it as a sequence of bits. Huh? So we said a bit sequence is an ordered sequence of n bits, and that is called the bit sequence. Yeah? So just a couple of bits in a sequence, and then if you want to set or get bit 42, you just go to that sequence, get or set it, and that's basically how we represent it. Now I'm hiding that information. I'm hiding how those bits are represented, and how do I do that? I put this data structure into, I shield it by using a function. And that's basically what I'm doing on this slide. I'm saying, okay, now I'm defining a bit sequence function that's shielding how I access those bit sequences. So the difference here is that this is a function now where you can input a position basically for such a bit, and then this bit, so this is a get version of that, and then this function returns whether this bit is set to true or not. And with that I can completely hide what's happening underneath. And then you can use these bit sequence functions in our p-encoded bit sequences that we used above, but it's just replacing the sequence with such a function. So what is run length encoding? I mean, the software engineering thing, of course, is that you can drop in any kind of compressed versus uncompressed bitmap. That's how you would do it anyway. You wrap it, you have an API, and you hide how you represent the bits underneath. Yeah? You never allow direct access to the bits, but always go through an API like that. You can hide how you represent the bits internally. It's just good software engineering practice written down on the slide, or sketched on the slide. Okay, so what is run length encoding? That's a method, I think it was first used in communications and computer graphics. Computer graphics back then when you only had pixels in two colors, white and black. And it works as follows. Assume a bit sequence like this. Yeah. You basically encode the repetitions. So you say, okay, here I have 4 bits that are set to 0. So I represent that as a tuple that is the value of that bit and then the number of repetitions. So the sequence of individual bits is replaced by a sequence of these tuples. Always the value of the bit and then the number of repetitions. So 4 zeros become 0, 4. 2 ones become 1, 2, 2 zeros become 0, 2, and so forth and so forth. And like that, you can encode this sequence as that, as those tuples. Here's another example. Sequence 2, 2 ones gives you 1, 2, 3 zeros, 0, 3, and so forth and so forth. Yeah, that's called run length encoding. And of course, what's the trade-off here? Yeah.
The number of beats we need to store the number of repetitions, sometimes maybe even more than the repetitions themselves.
Right. Yeah. So as with any, that holds for I think all compression methods I'm aware of, you may apply the compression method, but you may create something that's bigger than the original data, yeah? Because the compression ratio you're attaining is just a problem. Yeah? And then here, imagine you had a bit sequence 0, 1, 0, 1, 0, 1 or something like that would completely ruin this idea. Yeah? So the underlying assumption here, or the underlying hope is that there are repetitions in the data. Yeah, that's the same for all compression methods. The hope is there is redundancy that I can represent more efficiently than just representing it uncompressed. Yeah? And that's the same happens here. Okay. Yeah, and then of course you can think about, okay, how do you represent these things efficiently anyway? Yeah? Of course, in the Python world, you could say, oh yeah, I make that really a tuple, I make that, yeah, a bool, comma, an int value, yeah, and then you get into problems pretty quickly. So for instance, yes, if you have these tuples, how did I define that? The value of the bit, yeah, that's bool, comma, the number of repetitions, so in something like that, bool, and then whatever, maybe it's an int 32 or it's an int 16 or whatever the type is in your programming language. So here you want to be careful because that may introduce a lot of redundant bits. So typically when you go down that rabbit hole of compressing, you quickly end up bit fiddling and making really sure you just, I just use 3 bits here, yeah, and then, okay, this is 1 bit and so forth, and you try to make this as space efficient as possible. Yeah, so that's a trade-off you want to consider. So for instance, you could analyze how many repetitions do I have at most in my data set, and based on that you could set the type, for instance. Yeah, if you know, oh, the highest number of repetitions I have here is whatever, 65K, yeah, then 2 bytes is enough for that to represent. Yeah, you don't need more than 2 bytes for that. Why we always use 4 bytes if the first 2 bytes are 0? Yeah? So that's, you can optimize that representation in many different ways. Okay, so I wrote a sloppy sentence here. Adjust this function accordingly. So, okay, now I have this run length encoding, but what does it imply for this function giving me a specific bit or allowing me to set a specific bit? And there are 2 ways to access those bit lists. So typically they're used as a whole. You have 2 huge bit lists and you do an AND operation or something on these 2 bit lists. We'll get to that in a moment, but so we read them sequentially, but what if you want to access this stuff at a specific position, say at position 12 or something like that? And you could create an index on that if you wanted, and the index would look something like this. You could say, okay, those 2 entries of my sequence represent 6 underlying bits. 4 plus 2 is 6. Those represent 5. Yeah? So some of that represents, not 13, right? Okay. No, I miscalculated here something. 2, 1, 5. This is 6, so this should be 11 actually, right? 4 and 2 is 6, 2 and 2 is 4, this should be 10, and this should be 21. Okay, then that's correct. Yeah, so basically you have a hierarchical grouping of the number of bits that are represented in the subtree. And that you could use for an operation like, whatever, get bit at position number 10. Yeah? Then you simply do binary search. You start here, okay, 10 is smaller 21, you go here, because this represents the first 11 bits, and then you could go, then you go to the right, of course, and then you end up here saying, okay, that is the bit I'm actually interested in. That's how you could access such a bit. Yeah? But that's very untypical. I'm just saying this is how you could do it. The more interesting thing is sequential access, because it's, I will also show more examples in a moment how these bitmaps are used. I mentioned that already last time. It's read mostly or read only scenarios. But this is a typical thing you want to do with such a bit list, and that is you want to combine two bit lists. Yeah, but you want to take the whole of bit list S1 and the whole of S2 and compute a new combined bit list. And now let's assume that both bit lists are run length encoded. So it's the same example as on that previous slide. And what I do here to visualize this, I put it on an axis, and geometrically I adjust the distances. So here you see this is of size 4 because this represents 4 bits. This is of size 2, size 1, size 6. That is for sequence 1, and for sequence 2 it's a similar thing. Okay, here this represents 2 bits, 3, another 3, another 7. So both sequences have the same length, the same number of bits underneath that are represented. And now what you can do in an algorithm to combine these two bit sets is to interpret the boundary in between these entries. This is a boundary here as a cut. So this cuts this axis geometrically, but you should also interpret it as a cut on the other axis. So I'm cutting both. Yeah? So whenever there's two entries, either an S1 and S2 cutting the axis at that point in time, because there's a change. Yeah? So basically it can only mean in run length encoding that, okay, previously it was 0, now it's 1, or previously it was 1 and now it's 0. Interpret that as a cut. So you partition your data with that. And that means that in this particular example, the first cut will happen here. Yeah? So this is 2 elements. Here I'm still in this element, the 4 elements. But you could now break this 0.4 into a new entry 0.2. Yeah? And within this block, you can combine those 2 run length encoded elements directly. Yeah? There's no magic of counting back and forth, where am I in the one element, where am I in the other element. You just break this 0.4 into, here in this case, 2 new elements. So 0.202 is a redundant representation, of course, but if I aggregated those 2 elements, I would end up again with 0.4. But the elegant thing here is that now you can delegate those calls directly to a function computing that operation, and that will return another run length encoded element, of course, because whatever the result of that is, the result can only be true or false for all of the bits here I'm using. Yeah, so clear? Yeah, so whatever the operation is, be it that this is an AND or an OR, yeah, the result is false for all of the bits or true for all of the bits. And that's what we're seeing here in this example. So here I'm using the Boolean AND operation, and you see that, okay, what I compute as a result is 0.2. So 2 bits that are set to false is the result of that output. So like that, you can partition your data. That also entails that this is a streaming algorithm. So at no point do you have to load the entire sequence S1 into main memory or S2 into main memory. You can do this as a merge algorithm, basically, with very, very little memory requirements. And whenever you identify such a pair, you just do the operation, compute the result, and send it to the output. Yeah, so that's what you see here. I don't know, is that clear, the idea of partitioning the data? Yeah? No? Huh?
Basically, your memory has to be as large as the largest space between 2 cuts, right?
As the largest?
Memory has to be at least the size of the largest partition, basically, of the largest cut, right? Or can we also load like half?
No, I mean, maybe that's a bit misleading here. So the memory is always the same size, right? It's only these 2 elements, right? Yeah, it's just that's maybe a confusion with the geometric representation. So technically, you at all times you only have 1 element from S1 and one element from S2, and then you make a decision what to do with those elements for instance, cut them into smaller elements and feed those elements into the operation. So the memory requirements is really like nothing. You know? Very similar to what we had when we talked about external merge sort. Yeah, you only look at the top element for each of the streams and then you do something with that. Okay, right, so when you do that, partition it like that, and we actually, so in the code you will see there's a slightly improved variant of this algorithm, but I wanted to explain it a bit more conceptually here in the lecture. You actually don't have to physically split this into such a tuple. You could also do that by counting in the right way. If you find out, okay, this overlaps or doesn't overlap, you don't really have to create new tuples here. You can, again, improve upon that. But I think it's important to understand the principle of this algorithm, the principal idea of this algorithm. And when you do that for a specific Boolean operation, say an AND operation, you end up with these results. Yeah? Those are the results of those operations. And then you see the run length encoding on that is not perfect, yeah? Because you get two adjacent tuples with a 0 here. Yeah? It's actually 3 tuples with a 0. It's the same effect you have here. So what you could do here is post-processing again. It's a post-aggregation. Yeah? That's an aggregation algorithm that needs to look at the sequence of tuples, and whenever there is the same bit represented in the tuple, you just adjust the counter. You just add up the counters, and then you end up with a perfectly compressed run length encoded result of that. Yeah? Is that, yeah?
One question for the RLE format in general.
Mm-hmm.
So whenever we have those tuples of bit value and number of times bit value occurs, we know that the first component of the tuples will always alternate, because otherwise we wouldn't make these tuples.
Yeah.
So essentially we could just...
Yes, that's true. Very good. Yeah.
1 or 0, and then
Yeah.
just the number
Yeah.
of times.
Yeah.
Always copying the first.
Yeah, that's true. Yeah, so basically, the only thing you need to represent is you have to signal, okay, what is the value of the first bit? Yeah, and then if there's a new entry, you could directly interpret that, yeah, the bit is flipped. Yeah, very good remark. Yeah, so by that you could skip basically, yeah, you see it here in those sequences. Huh? Yeah, 0, 1, 0, 1, 0. It must flip by definition, otherwise it's not perfectly compressed. However, a bit more general and more careful, for instance here, I use a trick that to balance a tree, I have two tuples that both start with 0 in the sequence, yeah, which is not perfect compression, but allows me to balance this tree a bit better. And the same effect occurs here, of course, yeah. I would have to be careful if I followed that, yeah, but you're right, yeah, it would be an easy way to save storing that bit. Good. What else did I want to say about this? Any questions? Clear? Okay. And the variant of that, or like kind of the simplified version of that, it's what's called word-aligned hybrid bitmap. So let's start with this example again. So we have the city attribute. We have for all the different occurrences. So this is already, oops. This is already dictionary encoded, obviously. So we have integers that appear here. Those integers appear here in those columns. So I have these d-bit lists, aka sequences. And that is a bit sequence for the attribute value 88. And then what you do here is you rotate that, and for the purpose of this experiment, I'm adding more data. So in this toy data here, yeah, here I set ... not specifying how many tuples I have in this colleague's table. I'm just wondering. These are super old slides, and it's still allowed to say 88. So sorry, there's no political implication whatsoever, if you're wondering here. Yeah? I'm sorry. When I did that, I wasn't aware of that, and maybe I should change the number. Doesn't mean anything. Okay, so I'm displaying here 63 bits per row. And I have tons of bits, so it's many rows here. And now what I'm doing is in word-aligned hybrid is I don't compress by looking at sequences of bits, but I compress in blocks of 63 bits. Yeah, so it's kind of the simplified version of run-length encoding. And the idea is, whenever there is, so if I look at the first 63 bits, yeah, everything that's marked in yellow here, yeah, I look whether all of these bits have the same value in those first 63 bits. That's obviously not the case. We have these 2 bits set here. So if this is the case, yeah, so there's some are false, some are true, I say, okay, that's a literal. I really represent this stuff as is. And I do that by outputting a 64-bit word where this first bit is set to 0. And this 0 indicates that's a literal. That's literally the data that's following. There's literally the 63 bits following, and they should be taken as is. However, in a situation like that, where you have multiple 63-bit blocks that all have the same bit, I can output a separate type of 64-bit, maybe go back to the semantics here on the slides as well. We can show the semantics first. Yeah? So that's called a fill word. Yeah? So that was a literal word. We had before data bits 62 to 0, which is 63 bits. And now I'm using a fill word, that's the second type, and that has a fill pattern, which is a single bit. So I can use fill words for just ones or for just zeros. Then you could even reason about, okay, what if you had a fill word that's more than 1 bit? But I think there's hardly use for that. So that's how this method was divided. There's a variance of this method, said a couple of papers. That's not just one word-aligned hybrid. As for any data structure, there are variants. But the variant I'm explaining is using this 1 bit. And then the number of repetitions. So if you look at the example, what we're getting here, there was a literal. Now we have a fill word. So here we have this 1 signaling a fill word. Then this other bit, the next bit that's following is a fill pattern. And then all the blue stuff encodes the number of repetitions in the input data. Yeah, so here the number of repetitions, this is all binary of course, is 2. Yeah, so 2 63-bit chunks of bits. 63 times 2 bits that are set to 0, and that's represented in the single 64 bit word. Yeah, is that clear? So, and the same now occurs for the next input line, which, okay, we have a bunch of 1s and 0s here, so that must be literal, of course. We set this to 0 and represent the 63 bits as is. Then the next comes up. So we have 3 63-bit chunks. That's why we encode a 3 here, the number of repetitions. Again, the fill pattern here, and again, the signaling bit saying, hey, that's a fill word. And so forth, till finally there's another literal, that's represented as this. And that's how you can very efficiently compress these things, rather than looking at bits individually. Yeah, and actually the algorithm I showed before can be adjusted to that. You know? If you look at, no, here I'm going, here I want to go. Yeah, so you have a similar problem. Of course, for all of these things, yeah, for all of the operations you perform on compressed data, I mean, it's a general problem you have in databases. You cannot only compress bit lists, you can compress relations, you can compress indexes, you can compress whatever. And there's always the algorithm, okay, now I want to do an operation on compressed data. First thing you do is you decompress the data, then you do the operation, and then you compress it again. That's fair, that works all of the time, by definition. Yeah? I mean, if you have operations working on uncompressed data, then you're good to go. You don't have to implement anything anymore, because if you have those operations, it's just a matter of uncompressing, doing the operation on the uncompressed data and maybe compressing it again. But that's not the best thing you can do. Ideally, you want to do query processing, and that's what we're doing here. We do this AND operation on the compressed data directly, yeah? Because it saves CPU, but it in particular also saves I/O. If you look at these word-aligned hybrid things, here we go. Yeah, imagine you have repetitions like crazy, millions of zeros represented. And then you first decompress that. That's a lot of data that fills up your machine, and you don't want to do that. So you want to do that directly on the compressed data. Yeah? But of course, that's the second thing. The first thing you always do is make it correct. Yeah? Uncompress it, use the algorithms that are available for the uncompressed data, compute the result, and then maybe compress it again. But then the second thing to really make it efficient is to have algorithms that work on the compressed data directly, and then the results can be compared directly in end-to-end unit tests with the easy version, with the first version. Okay, yeah, so much about that. Right, yeah, maybe let's look a little bit into Bloom filters we do in the second part. Let's look a little bit at the use cases actually of bitmap operations. Yeah, because they not only appear in pandas, they appear in many places. In a very prominent place where they appeared first in the data processing was so-called star schemas. Star schema in the context of data warehousing, or online analytical processing. I think I mentioned that term before, OLAP. And the kind of schemas, the database schemas they used are not the schemas you find in the standard database. Yeah, in the standard database, everything is normalized, there's no redundancies and stuff like that. But back in the 90s, the problem was the schemas were big, you had dozens of relations. And if you try to do queries on these 20, 30, 40 relations, the result would never come back, yeah? Because it would take too long. The systems were using hard disks and stuff like that. So people did schema hacking. So what they did was they had a central table called the fact table, and around that they had dimension tables. Now let's call it D1, D2, D3, and D4, for instance. So a central star, so to say, yeah, and then the dimension tables around that star. And those dimension tables would represent semantics like whatever, customers, products, some sort of time dimension, and this could be geographic area or whatever department or something like that. Yeah? Yeah. And then when you did analytical queries, it was a matter of selecting stuff here on those dimension tables, but basically joining with a central fact table. So typically those dimension tables would be relatively small, whatever small means, but the fact table would be massive, millions and zillions of tuples. Yeah? And those were all foreign keys. So basically the fact table is organized, it has 4 columns, yeah, with the foreign keys, 1 to D1, 1 to D2, 1 to D3, and 1 to D4. The combination of that would be the key. Yeah? It's getting small. Basically those are the foreign keys here. And then here, that would be the measures, or Kennzahlen in German. So basically, if you sold a product to a specific customer at a specific time in a specific department, there would be an entry. Yeah, would be an entry, maybe with a price tag or whatever. Price 42, of course, but those were all foreign keys. Yeah? And another important property, that's why I said this was a hack. Those dimension tables were sometimes denormalized. Denormalized meaning there was redundancy. Yeah, so this wouldn't be the tables you would end up typically when doing proper database design. And that was intended. The idea was, I mean, if I normalized all of that, yeah, for instance, I don't know, maybe customers that's split up into more relations. Let's remove that. And maybe there's a more complex schema here, whatever the relations mean in this case doesn't really matter. Yeah, but maybe it's something like that. And now you did a huge analytical query. Yeah, each of those edges, of course, would end up, you would have to do a join on those things. Yeah? So the idea was to pre-materialize this data, so a subset of that schema was pre-joined, was pre-materialized. I mentioned materialized view at some point, into what was called a dimension table, D2, with potentially redundant information. But what I gained at query time was that I wouldn't have to join this stuff anymore. This was already pre-joined. Yeah, you see that? So what are the pros and cons of this approach, other than what I just said?
Pre-join those, you have to save those bills, and yeah, it doesn't take huge space because of the older communications.
What takes space?
Memory, saving space.
Yeah, but what exactly? What part of what I explained takes space, or it's a problem?
The pre-join table. The pre-join table.
Yeah, okay, right, sure. Because in particular, because I have redundancies, yeah, I represent data redundantly, so that's a stupid thing to do. We should never do that as a computer scientist. Go to industry, you see people do it like that. Schema hacking. Yeah, that's a drawback of that, obviously. What's another drawback of something like that if you pre-join or pre-compute the result to a join? Maybe you remember from the undergrad lecture or from some other place. Yeah? Yeah. This is called materialized view maintenance. So this is called a materialized view, or MV for short. And whenever this changes, yeah, you have to recompute the stuff. This will be out of date, of course. Yeah? And that is the reason why in these approaches, at the time, you still see it in industry, but it's still hard to understand. Now the button works. What people do is they keep a separate OLTP database. OLTP meaning that is the real database. This is your database, and that is where all your web application sits on top and does the changes the users operate on this database. But once every night, in those systems, you create a copy. You create a new version of your dimension tables and your fact tables, such that the next day when the manager hits the office, he or she can do analytics on the stuff. Slightly stale, slightly outdated, but that doesn't matter for this application because the intention was really to get the big picture. Yeah, the big picture typically doesn't change so much over one day. Yeah, that's okay to have slightly stale data. So there was a trade-off people did. Yeah, so the later the day, the more you would be, the staler the data would get, but then during the next night you would create a new version of that data warehouse. And of course, the night had to be enough to create that version, which was a problem sometimes, because the joins were expensive, there was too much data, and then you didn't have a new version, and then let's hope you still had the old version. If you deleted the old version already, you had no version and there was no analytics. That was another option. But there was a trade-off here. Now, how did I get there? So bitlists. Okay. Now, in these scenarios, actually, yeah, and maybe just before going to that, I can add another footnote here. Yeah, so this is called a star schema. If the dimension tables, here the dimension tables are denormalized, so you have redundancies, a single dimension table. If they are not, if they're like that, the schema is called a snowflake schema. Snowflake schema. And actually there's a famous database company called Snowflake that does this kind of technology actually. And if you connect multiple of these schemas, be it star schemas or snowflake schemas, so you could imagine that, for instance, the dimension table is used by multiple fact tables. Assume there's a second fact table, maybe reusing that and some other dimension table. This is called a galaxy schema. Galaxy schema. Yeah. And in a big company, you would have many or very large galaxy schemas, and then the challenge in query processing is to, you just have this time window overnight to process this stuff and get the things right. So there are many, many technical challenges here. Okay, but in these scenarios, you're in a read-only world. It depends on what you define, how you define world, but if you just look at this is read-only. So when you do the analytics on your snapshot of the data, it's read-only. Of course, you update it every night in batches, then it's not exactly read-only anymore, but while the manager or whoever is sending queries to these galaxy schemas, it's read-only. And that means bitmaps make a lot of sense. Yeah? So when you create this snapshot, of course, you can create all kinds of crazy indexes, and you will be creating bitmap indexes, individual bitmap indexes, but also combinations of dimensions and fact tables. Yeah? And how that works in detail, we will see in the break. I will scribble a more elaborate example on the blackboard in the break. So I scribbled a bigger example here. So that's the situation. We have a fact table, and the fact table here has only two dimension tables. I scribbled down one only. So here's the fact table has a foreign key 2-dimension table 1, and a foreign key 2-dimension table 2, not shown here on the blackboard. Yeah? So we have a couple of dimension tables surrounding the central fact table. For each dimension table, there's a foreign key to that dimension table. And the fact table, the primary key of the fact table, is the composed key of all those foreign keys. So here I have d1_id and d2_id build the primary key of this relation. Sometimes you even add more attributes, but in the general case, that is your primary key. Now you have all kinds of entries here. So dimension 1 in this toy example only has 3 rows. Here are the IDs, here's a name attribute, here's a blah attribute. And like that, you only have 0, 1, or 2 appearing here in this column. What I also scribbled down is a row ID. Row ID in the sense, imagine this were represented as an array. You have slots from 0 to whatever, and -1, so that's the first slot in that array. Yeah, but we talked about that when we talked about virtual memory and prefix addressing. So all database systems I'm aware of have some sort of internal ID of a row. A physical ID you should never ever use for query processing. Fun fact, you can even use that in Postgres. There are famous bugs that occurred because people used row IDs in query processing. They made the assumption, for instance, I want to have the row that's after that other row in your store. This doesn't have semantics in SQL. There's no such thing as adjacent, unless you force sorting. But if the model we have in our heads is a set, unsorted, the order doesn't mean anything. But there were some famous examples where people really used this physical address to query, and then, if the underlying order of the tuples change, you're screwed, of course. Yeah? You should never do that, but technically, you would be able to do that in many systems. So here's my dimension table. And then, of course, I could create bitmaps. Yeah? So here's a bitmap on name, for instance. And here's a bitmap on blah. So it's 3 different values. So I have these bit lists, bit sequences, basically here. Yeah, so 011, 100, 001. And I can do the same thing here for the blah attribute. There's only 2 and 1 as data values, so I only have 2 bit sequences, 110 and 001. Yeah, that's what we had also on the slide so far. And of course, with that, you could do operations like identify quickly within a dimension, if you have multiple conditions in particular, which of those tuples take place. Yeah? If you have a similar row ID concept, and basically the row IDs here match, yeah? You know this is position 0, 1, 2, yeah? Same here, 0, 1, 2, and that must match to your data in the dimension table, otherwise you can't do any meaningful query processing. But once you can do that, you can answer queries like name equals Hans and and whatever blah equals 1. Yeah, and then you can intersect the 2 bit lists, Hans, this one, 100, and blah equals 1, 0, 0, 1, yields 0, 0, 0. Yeah, which means none of the rows actually qualify in the dimension table. Yeah, which means there's no result in the database with this condition. Okay, so that's what we had so far. But another optimization, I think Oracle pioneered that. And unfortunately, with all of the techniques I'm explaining in this lecture, there are many patents in this world. So the market for database technology is insane. At billions of dollars every year. And companies, unfortunately, tend to create nonsense patterns, or sometimes patterns are also meaningful. But many of the techniques I'm explaining today are patented like crazy. Yeah? So if you want to create a company around that, be careful. In particular, this bitmap stuff, there are many patents in this world. Yeah? And these patents overlap, and then similar, 2 different companies file the same patent, which overlaps like crazy, then they sue each other, or they make deals and stuff like that. It's really crazy. It's not great. So I'm not a big fan of that. But what I was trying to explain is an extension to that. So of course, here you could now filter quickly and find out which are the tuples that qualify for the dimension tables. That would be very efficient, but the variant of that was bitmap join indexes. And what is that doing? Here, you wouldn't only keep bit lists of length number of tuples in the dimension table, but here you would extend those bit lists to the length of the fact table. Yeah, and if you combine that with compression, what we explained before, you would end up into something like that. So assume we make this a bitmap join index. Now we would say Hans, and the bit list for this would be, I set the bit to true if the row ID here is 0. This is a foreign key to this relation. Don't confuse it now with a bit. Maybe I use a different example to make it easier. Let's make it Tom. Let's create the bitmap join index for Tom. Bitmap join index for Tom. So that would be all the columns that are set to 2. So that's this one. And that's it for the moment. 0, 0, 0. Yeah? See that pattern? You can do the same for each and every, or you can also do it, you don't have to do it for all of the dimension tables, but for instance, it could be a great idea if you always filter on on like 2 of of all the dimension tables that exist in the largest schema, you could say, okay, I mean, I'm filtering very often on these attributes, so rather than doing the standard query processing by using bitmaps on the dimension, selecting the rows, and then joining those rows with a fact table, I rather keep a bitmap like this, a bitmap join index that does what? What is the semantics of such a bitmap join index? When you look it up. Yeah, we could also draw another one. For instance, we could say bitmap join index on blah. So this basically is name.tom if you want. Name.tom, and this is blah.2. Yeah, everything where the dimension table 1 in attribute blah is set to 2. That means all the ID set I get is the ID 0 and 1, which means I have to mark all those rows where this attribute value is either 0 or 1. Yeah? So that would mean 1, 1, 1, 0, 1, 1, 1. Yeah? So what I'm basically doing is in my head, I'm joining the 2 relations. Yeah, to compute the result of such a bitmap join index, name.tom, I'm basically joining this fact table with a dimension table. It's as if you were extending this by an extra column. Yeah? Basically, that's also called tuple reconstruction. So basically, if you do that for blah, you could basically, blah.2, you could collect this specific value of blah.2 for this particular row. Sorry, I wanted to say the attribute value of this blah attribute of dimension 1, which is 2 here. 2, 2, 1, 2, 2, 2, right? Only here it's different. And yeah, so basically it's like attaching the value redundantly of this attribute value of D1 in my head. I don't do that physically, but once I did that, based on that, I create the standard bitmap, the standard bit sequence. Yeah? Now I can again argue along equality and say, okay, so for which rows of my original fact table is it the case that the value of blah equals 2? And that is what this bit sequence shows. Yeah, you see that? Yeah, so first joining, or you could say you first attach the attribute value. You shouldn't do that physically because it's crazy redundancy. Yeah, but I'm doing it in my head kind of, and then based on that I evaluate the condition. The condition is equals 2, yeah, and where that equals 2, I set the bit, and otherwise I set to true, otherwise I set it to false. Yeah? And like that, I get something like that. What can I do with that? What's the difference to what we did before, where we had these bitmaps on the dimension tables? Yeah, let's be more specific, because we already were very quick in filtering things with the standard bitmaps. Well, what is the difference I can do over what I had before? Yeah? Yeah, it's on the joined table. Basically, I don't have to do the join anymore. If the goal of my operation is just to filter out stuff rather than displaying stuff from this dimension table, I don't have to do the join between D1 and F anymore because the result of the predicate of the where clause is already encoded in the bitmap join index. I save an entire join. That's an important property here. Huh? And if this can be represented efficiently through some whatever compression technique, and you have the entire night to create this stuff anyway, that might be an interesting technique, unless Oracle sues you. Yeah? Be careful. But they first have to prove you're doing it. So that's why companies then use fancy names on your websites. Oh, we use this tralala, new fancy technique. And then you have very, very shady or vague explanations of stuff. But when you think, oh yeah, it's the bitmap join index, isn't it? Okay, right, so that's the first thing. You save the join if you don't have to show attributes here. So what's the second thing you can do in contrast to what we did before? If you think about it, I mean, it's typically you don't have conditions just on one dimension table. You have it on multiple dimension tables. Yeah? And if you have a bitmap here, bitmap there, there, and there, compared to what I'm doing here. Yeah, that's a huge thing. That's a big thing. Yeah, because now if I have a bitmap join index here referring to dimension 1, I might have another bitmap join index referring to dimension 2. But hey, they are defined on F, so I can again combine those bit lists like we did for the standard bit lists to compute and, or, not, and whatever you want to have as a Boolean operation. And that's a big thing. So you save the individual joins, but you can also directly combine these things. You end up with a bit sequence of length number of tuples here, and then you can basically scan this relation and filter out the stuff directly with that bit list. Yeah? So that's a huge thing. It was a big game changer for these systems, actually. Yeah, that's bitmap join indexes. Yeah, so far? Okay. Yeah. Or maybe let's go to the overview again. So we started here today. Yeah? So I said there's uncompressed bitmap indexes, there's compressed and lossy. Compressed, there's lossless and lossy. So this is all about lossless compression, I explained so far. In particular, run length encoding is lossless, whether you do it bitwise or you do it with word-aligned hybrid. Yeah? This is lossless. But now let's look into lossy, yeah? If you want to do lossy compression. And here the idea is really, okay, I don't have that much space. And compression, either I'm too lazy to implement compression, I don't want to use compression, or I don't even have enough space if I come for the compressed bitmap indexes. So what can I do? And there are still things you can do in that world. No, this is just okay. And this is called a Bloom filter. And the idea of that, oh come on, this iPad is crazy today. That's called a Bloom filter, and how does that work? So the idea is, the idea is very similar to have in a standard hash table. However, in a standard hash table, you typically store the values. Yes, you have an array of values, and you have a hash function telling you where to store that value. Yeah? And then you have chained hashing and open addressing and stuff like that. Here we just have a simple array of bits in the middle. There's no overflow chains whatsoever, and there's no open addressing whatsoever. It's just about an array of bits in the middle. They're also referred to as buckets in Bloom filters. So they're numbered from 0 to m-1. I have m, capital M, number of buckets. What I also have is hash functions, a couple of hash functions. So you can analyze these Bloom filters, and then you see the more hash functions you add, the better are the properties. We will get to those properties in a moment. Let's just go through the example for the moment. So when I say insert here, I'm not actually inserting the value here, or the key in this case. So the key 42, 43, 42, this integer. So this key is not actually stored in the Bloom filter. It's just marked. The Bloom filter marks it, yeah, or records it that it might have been marked here. So what I do is, to insert this key, I have my 3 hash functions, and the hash function 1 returns a particular bucket, say 12. So I set this bit to true. The second hash function returns bucket 7, I set this bit to true. The third returns 32, I set this bit to true as well. Let's add another value, and another key. So here 983764. Again, the different hash functions yield 3 different buckets here. I set all of these values to true. Now there's a third operation, set bit 12781, and this again maps to 3 buckets, and then here you already see the collision. Collision as in standard hash tables. This bit was already set by a previous insert. Now I'm setting it again with a different key. So which color has this bit? Not clear, because this color, I mean, it was set by 2 operations. However, I mean, I just represent it as a bit. I don't have the information about color anymore later on. That's gone. I just have the bit is set to true. And I have no idea who the heck set this bit. And that's an important property of a Bloom filter we will see in a moment. Because the semantics in the Bloom filter are not precise. It's a probabilistic data structure which has the following semantics. So for a hash function, so if you now look up in the Bloom filter, so we basically again, if you want to look up 42 or something like that, we feed the 42 into the different hash functions, and if any of the hash functions point to a bucket that is where the bit is set to false, the Bloom filter guarantees that the value is not there. It cannot be there by definition. Otherwise, it would have been set in the first place. However, if we look up a value and we see that all of the hash functions point to buckets where the bit is set to true, this means that it may be in the bitmap. It's not guaranteed due to these collisions. It could be that other inserts set those bits, yeah, and now we are tricked into believing, oh yeah, this key was also inserted. No, we don't know. It just means maybe. It may be there. Yeah? So the Bloom filter allows us to save space in the sense that it can tell us it's not there. Don't go here. Don't look here. You don't have to go further along this road. There's nothing to find here. Yeah? But if it says, yeah, it could be, I'm not sure, maybe you take a look yourself, maybe it's there, I have no idea, it could be there, so I can't exclude the possibility that it is there. Yeah, that's the semantics of the Bloom filter. And you see it here, here's another example for the lookup. So that's the value we inserted so far. We see all of these bits are set when I feed that into the hash function again. Yeah, so it could be there, and I think that's something 983764, we inserted that before, right? Yeah, that's the one we actually inserted, so that's a case of something we actually inserted. Now we look up 2956. That's a case where we have some zeros. Yeah, so it's 1 0 is enough in those hash functions to guarantee, hey, it cannot be there. Yeah? And here's another one that returns all ones, 7431, and I think that's something we never inserted. If you go back, yeah, right. Yeah, we inserted this, that, oops, and that, but 7431 was never inserted. Yeah, but still the Bloom filter is not able to differentiate those cases. Yeah? So now, so here it doesn't really help. Yeah, and then you can do all kinds of analysis on these Bloom filters, and what you want to minimize is the false positive rate. So a false positive is exactly this one. So Bloom filter, false positive is misleading a bit, the name, but that's how it's called in literature. So the Bloom filter tells you maybe. Yeah? I mean, the Bloom filter is precise in the sense it never says yes. Yeah, positive. Yeah, and that's a misleading thing here with this name false positive. Yeah, the Bloom filter never says it's positive. It just says yeah, maybe. Yeah, but your interpretation when you use a Bloom filter might be yeah, it's positive. The Bloom filter says positive. Yeah, and then you do some other work and find out no, it's actually not there. Why did the Bloom filter tell me? Yeah, so that's a false positive in that terminology. Yeah. And then basically, you have parameters that you can fiddle with. You can basically play with the size, so the number of buckets. You set that in the relation to the number of inserts. And then you can try to come up with a number of hash functions that are ideal for a use case. And then you can do an analysis and actually optimize on that. I think here's a result of such an optimization approach, which already does some simplifications you can question here and there. So for this to work, you really have to make sure that the hash functions create a uniform distribution. Yeah, as you probably learned in the algorithms and data structures course. So hashing only really works well if the stuff is hashed, if it is distributed over that array. Yeah? If you have hash functions that cluster the data in a couple of buckets, you're screwed. Yeah? Assume a hash function that always returns bucket 42. Yeah? Then you have an overflow list in the standard hash table, you don't gain anything. So a good hash function distributed like crazy. And that's one assumption you must make, which is not always true depending on which hash function you're using. Yeah? So a footnote, to analyze hash tables, it can be a very good idea to analyze the distribution to see whether your hash functions actually do a good job of distributing the data. Yeah, and the other thing is, and that's an unknown often, I mean, sometimes you simply don't know how many elements you're going to insert. I mean, if I know that in advance, then it's easy, but yeah, you keep on inserting, and all the bits are set, yeah, then the Bloom filter doesn't help. That's, if you remember and attended the Christmas lecture, that's actually what I visualized in that tree. Where was that? Here. Yeah, he had a poor man's Bloom filter. But here these crystal balls, they are drawn initially, and then they get thinner and thinner and disappear. And when you look into the code, you will see that the alpha channel, the opacity, is computed by looking at the number of bits that are actually set in the Bloom filter. The more bits you set in such a Bloom filter, the less useful it becomes by definition, because no matter what you look up, it's always true. Yeah, the Bloom filter will always return maybe. That's not the kind of information you want to have. You want to have the Bloom filter to say no, maybe, no. That's the kind of information you want to have from a Bloom filter. Yeah, so tweaking that and setting the parameters right in a real implementation, yeah, it depends on looking at workloads, analyzing, yeah, also keeping track of how many bits are set in the Bloom filter, or maybe you have to resize a Bloom filter, like with hash tables. The same problem, yeah? Resizing in a hash table. You start with an initial hash table, and then you keep on inserting and you see, oh, this is not going to work, my performance goes down like crazy, the overflow chains get bigger and bigger, or on open addressing, you don't find any space anymore. Aha, I have to rehash the stuff. Yeah? Same happens here. Yeah? Depending on your workload, you might have to rehash and create a bigger Bloom filter. Yeah. Yeah, you can also compute the number of optimal hash functions given that you make these simplifications and uniform assumptions. Yeah, so bitmaps and Bloom filters are both very useful techniques to evaluate where conditions. They are space efficient and can be additionally compressed. And Bloom filters are probabilistic, yeah, but tunable for many scenarios. And maybe we revisit one of the scenarios. Or maybe it's up to you. So where would you use a Bloom filter? Where would you use a bitmap? And that's now the interesting question, right? Can you come up with scenarios where we can write so let's say bitmaps or uncompressed, or let's say I mean, for uncompressed bitmaps, if you never worry about main memory, like pandas, data stuff, you use it uncompressed, who cares? But let's assume we have here a column bitmaps that's either uncompressed or lossless, like in run length encoding in word-aligned hybrid, versus bitmaps that are lossy, yeah, Bloom filters. So where would you use which of those? What are typical use cases? What are use cases for those? Any idea? Some of them we mentioned, right?
So run length encoding, we do different things when we have very sparse data. Bitmaps, in general, I assume that the lossless compression capabilities include parallel to accuracy and don't have big enough data.
Right, accuracy, perfect accuracy, or perfect precision, how you want to phrase it, because the bitmaps will tell me, yeah, it's like that or it's not like that, there's no maybe. Yeah, accuracy, precision. Very good. Other ideas?
For the lossy bitmaps or Bloom filters, you would have to do, for every maybe decision, you would have to do some post-processing step to check what's actually there. So
Yes.
check about the run, if you care about the runtime, this could be a drawback of using lossy bitmaps.
Yes, yeah, and that's also an important trade-off you should factor in when setting the parameters of your Bloom filter. What is the price I'm paying for a maybe? Yeah, what is the price I'm paying if it's a false positive? Yeah? So Bloom filter falsely claims, it doesn't falsely claim, it says it maybe that you should do the work. Yeah? So there's at least a trade-off with post-processing should be worth it. Yeah? Yeah?
I guess with the lossy compression, we could calculate how filled is assuming we have a perfect hashing function, we could calculate how filled is the hash table, and based on that, assuming we have a perfect hashing function, we could calculate what's the probability of actually having a true positive.
Yeah, you can do, yeah, because for every hit, it's basically if you have like m buckets, yeah, the probability of hitting the bucket is a bucket where the it's set as 1 divided by m, and then you can do all the probability stuff. And so you can see that. I think I have links in the slides to that where this is computed. Again, all under uniform assumptions and stuff like that. But with that, you can compute the false. Didn't I have a slide on that just now? Here, that's this false positive rate. Yeah, that's a false positive rate, yeah, and that you want to bring down like crazy. And you can compute that based on your current number of buckets and the number of bits that are set and the number of hash functions. You can compute exactly that, and that gives you a number, and that number you can basically use to make a cost estimate. Okay, what is the price of my false positive rate? Am I willing to pay the price? If not, I better increase the size of my Bloom filter to bring down the false positive rate, or I add another hash function, or and so forth and so forth. Yeah? That's the kind of thing you do. You could actually measure the false positive rate. In the practical implementation, that would be way better. Yeah, because if you just making that up, but I think it makes a lot of sense. Yeah, because you do some sort of post-processing, and in post-processing, you can collect the information whether you found it or not. Yeah, so you can actually count for, okay, man, how many lookups am I doing in my Bloom filter? How many of them actually lead to stuff that's there? How many not? Yeah, that's your empirical false positive rate. It's so much better because you can factor out all of the fluff with hash functions and properties and tra-la-la-la-la. You have a real number. You know, okay, it works, it doesn't work, and you exactly know the costs of post-processing or doing post-processing for false positives. Right, but what is another thing? Can you think about other tags, other labels, or other situations that may help decide whether you go for the left or go for the right technique? Yeah?
So if we can accurately include the information about false positive rate and take it into account, then if we do analytics on very, very huge data sets, it might be a good idea to use the lossy compression for relatively quick-ish results. If we can, with the assumption that we can accurately post-process and take into account the false positive rate.
Yeah, but you can always also do a standard compressed bitmap, right?
Yeah, like if we have a big enough data that it would be unreasonable to do that on the.
Yeah, what do you mean by reasonable in your answer?
Like if we need to have real-time-ish analytics, and we have, we have a huge data sets we're working on, for example, analyzing the network of Azure.
I mean, that's true. It could happen that evaluating that is faster. In particular, if this sits in main memory. In contrast, you have these crazy run lengths, word aligned hybrid, whatever compressed stuff that maybe doesn't fit into main memory, whatever, and it takes more time to. It could happen. Yeah? But the other thing is really main memory constraint. Yeah? Main memory constraint. Yeah, you really have a scarcity with the available main memory. Yeah, and you try to balance that. It's the same as with hash tables, as I explained the other day. Why do you use a hash table? Yeah, because if you have keys from 0 to 4 trillion, I mean, I could just allocate an array from 0 to 4 trillion. Who cares? Yeah? But maybe it's not so resource friendly. So you try to compress it into a smaller array in the hash table. That's what the hashing is actually doing. It's all a form of compression in a way, and you do the same here. If this trade-off is still okay with your application, that's fine. Huh? But typically, it's some sort of memory constraint you're running into. Yeah? And that's also, but you often see these things in scenarios. If you think about indexing, I think I also scribbled that on the blackboard the other day when we talked about indexing in the Christmas lecture. There are these scenarios where you don't update in place, yeah, where you do batch updates. I had that in the Christmas tree as these candles. Yeah, last August buffer tree. These candles are buffers. Yeah? So in every node, I have this extra buffer. So I keep a buffer of insert operations, and then I don't push these inserts down immediately. Only if the buffer is full, I push it down a next level. That's what I explained before Christmas. And a very simplified version of that is to have a batch or a differential file or differential index, where you keep your insert operation. So this is kind of the read-only variant of the index. This is the read-write additions to the index. But now when you do a lookup to such a structure, which is split up into multiple structures, so where do you look? Yeah, what do you want to do? Typically you're in a situation where here you have very fast queries, and here you're screwed. Yeah? In the worst case, this is a linear structure where you have to do a linear scan over the elements. You don't want to do that. That's expensive. So here, a Bloom filter could be a very good idea. Yeah? So you first ask the Bloom filter, hey, do you happen to have anything in your differential file? Yeah? If not, oh yeah, I can ignore that. I do my lookup only here. Yeah, or sometimes in these structures, once you look it up here, you don't have to look it up there anymore. But if the Bloom filter says maybe you pay a high price for this post-processing, for scanning such a differential index. And that's something you really don't want to do. No? And that is why in these kind of situations, yeah, where you collect extra information or batches, Bloom filters are often used. No? They're very flexible here. Yeah. Do we have all the trade-offs? Bitmaps, uncompressed, lossless, sparse data, accuracy, precision, safe joins, yeah, bitmap join indexes. Sparse data, accuracy, precision. Yeah, I think that's complete. Here's a trade-off, speed, main memory, constraint. Yeah. Also for situations where you don't really know the domain, yeah, if you think about that. I mean, the bitmaps, if you do an insert here, yeah, so in particular in these situations, you keep on inserting, new keys come in, and maybe you don't really know what the keys, in which domain they sit, are they large, are they big keys, so the hash function will handle that, everything is fine. But here that may be more tricky. Oh, a new value comes in, I have to create a new bit list, stuff like that. Yeah. So bitmaps typically are a great idea if you see all the data in advance and then you optimize on that. Yeah. But if it's more a dynamic situation, I would tend to this side. Again, depends on the use case, but bitmaps is really more like read-only scenarios. This paddle data set, iris data set is read-only. Read-write data. Yeah? All right. Okay, yeah, that's it about bitmap indexes. So very powerful technique. So I invite you also to look at the code we implemented. So that's a lot of code. File system changes. So I don't care about this one. So one of my students implemented all of this actually. Bitmaps compressed and uncompressed, in particular the word-aligned hybrid with the correct semantics. It's a bit crazy. It's because the implementation is pretty long, even though we tried our best and did many review cycles. So don't worry. Yeah? So we don't ask about these details in the exam, just for the ones that are interested. But of course, the core idea of the algorithm I explained how to intersect those 2-bit sequences in word-aligned run length encoding, that's something we might ask about in an exam, of course. All right, that's it for today. See you on Friday. Oh.
One question for Bloom filters. Isn't it the case that the standard Bloom filter doesn't support deletes? Because we could accidentally delete something else.
Yes, very good question. So why does the Bloom filter doesn't support deletes? So assume, maybe go back to the slide where I mean, this is akin to, I want to delete the yellow one, but not the cyan, whatever the color is here. 1, right? And I can't do that because the semantic, I lost it, I just have the bit. Yeah? So for that, you could do what? Yes. Yes, counting Bloom filter. Yeah, that's an extension. Here then you have more than 1 bit and then a certain range of integers. Let's say you use 4 bits. Yeah, then the power of 4 bits could be represented. But I would argue you still mustn't delete anything that wasn't inserted, right? So you need to keep track of what you inserted in order to be able to delete. Yeah. Not sure, that risk is worth the trade-off. So maybe you want to have an extra structure to store what you deleted? Probably, right? Because I mean that has to be an assert. Assume you have that in production and you really delete something you never inserted. Yeah, I mean that's I wouldn't risk that actually. Yeah. So maybe delete would be really making sure that this was inserted before. Yeah. I mean you're right. It's kind of more like an append only or insert only thing typically. That's how it's used. So delete is can be difficult. Yeah. So counting Bloom filters is something where you can do things, but again you have to be careful. Okay, so let's see you on Friday. Thanks.